Good afternoon, everyone. So, in this presentation, I'll talk about differences between DPDK and ODP. So first, we'll take a look at why do we do this comparison? What's in it for us? Then I'll walk through a few of the main features that are different in ODP, and then we'll take some questions and answers. So first, why do we do this comparison? So from ARM side, we see that we see high customer demand for DPDK support on all ARM platforms. But DPDK was not designed originally with ARM platforms in mind. On the other hand, we have ODP, which was designed by our customers and partners to work well with all the available ARM platforms. So the question that we are asking is, why not take these ODP features to DPDK? Why can't we add those features into DPDK? And today, I see that our partners are already doing that. Our partners like Cavium and NXP, they are participating in DPDK community, and they have taken some of these features like event-driven programming model, and external memory pools to plug in the hardware accelerators for memory pools are already in DPDK. So from our point of view, it makes sense to accelerate and help our partners in order to achieve this. So with this in mind, let's take a look at a few of the features that I think are important. So the first feature that I want to talk about is the non-blocking queues. So I'll talk a little bit about the issue and then go into what can we do in order to take these features into DPDK. So today, DPDK supports lock-free blocking queues. So what that means is if there are multiple threads trying to communicate with each other using the queue, and if one of the thread goes away or it gets blocked for some reason, the other threads cannot proceed. They can't do any useful work. They are blocked at that point. But these queues are good. They are good. I mean, in terms of communication between data plane threads. They are fast, they are efficient, and that's what we need for data plane threads when they have to communicate to each other. But we have other use cases as well. We have use cases where the control plane thread and the data plane thread need to talk to each other. They need to exchange packets. So that presents the challenge that the control plane thread is running on the OS, and it can get preempted in the middle of a queue operation. So that would result in the data plane threads getting blocked. So this is the column the non-blocking queues solve. And today, ODP addresses that by having the non-blocking semantics to the queue parameters. So when the queue is created, it takes these non-blocking semantics, and the proper queue is created. So we can take this feature to DPDK, obviously, and I don't think we need a very high-performing algorithm here, because the control plane traffic is low in volume compared to the data plane traffic, and it's usually polished. So so we are planning to look at some simple algorithms to start with. We also have the algorithm implemented today in ODP. We can look at that algorithm. Then we also have some internal algorithms that we are working on. So I think this would be one good addition to DPDK from our perspective. So the next issue is packet memory optimizations. So ARM-based platforms, they have a wide range of capability. We have smaller SoCs that are at the edge doing, a few gigabits of traffic, versus we have these server platforms which sit in the core of the network. So many of our platforms have limited amount of memory. So what that means is memory optimization is a must for us. So to address this memory optimization, many of the ARM platforms support multiple memory pools, and each pool can have its own buffer size. So for example, I can have memory pools with 64 bytes, 256 bytes, 512, 1024, correct? You can usually configure what sizes you want. And then NIC picks the best buffer that suits the incoming packet, and it uses that way it results in the use of optimal packet size. Whereas in DPDK, currently it supports single memory pool. Typically, it supports it has 2K buffer size. So I think that wastes a lot of memory. For 64 byte packets, it's a lot. It wastes a lot of memory. And then if you have packets which are more than 2K, then you end up chaining the buffers, which requires additional CPU cycles. So in ODP, this is addressed using subpools. So ODP allows a memory pool to be created with subpools in them, and each subpool can have its own. It can have buffers with its own packet size. So the application, is allowed to create a single pool containing, buffers of different sizes. So I think, this helps achieve use of optimal use of the available memory, as well as it helps save CPU cycles when we have larger buffers. So today we have KVM and NXP participating in DPDK community, and I think this fits well with those platforms. So this is one of the features that we would like to take to DPDK. So the third topic that I want to talk about is the software scheduler. So here, today DPDK supports the event dev APIs. So I think that's a big achievement over there already for this transition. But the issue I have, or the issue that I see, is the implementation of the software scheduler itself. So today in DPDK, there are two software schedulers. The first one is called as the software scheduler for some reason, and that scheduler requires dedicated cores. So what that means is you have to have one core which just does packet scheduling. So I see several problems with that. The first problem is it's not suitable for SoCs with a small number of cores. If our partners have SoCs with 4, 8 cores, and if you end up dedicating one CPU for just doing scheduler, then you are left with less capacity for actual packet processing. So that's one issue I see. The other issue I see is this scheduling core will be either a bottleneck, as in you have a lot more CPU cores to do the packet processing, but you don't have enough capacity to do the packet scheduling. Or if you end up using multiple CPU cores for the scheduler, then you are in a situation where you have too much of scheduling capacity but less of packet processing capacity. So it is very difficult to achieve that optimal balance between scheduling and actual packet processing with this design. The other scheduler that's available is it's called as OPDL, Ordered Packet Distribution Library, but it just addresses a specific use case. It addresses the use case of pipelining model within DPDK, and it does not it doesn't support all the features that we expect out of a scheduler. So I think there is room for the distributed scheduler that ODP implements. So in ODP, many of our platforms have got hardware scheduler, and we don't dedicate any CPUs for that. But when we are using a software-based scheduler, we implement distributed scheduler. So the distributed scheduler runs on each packet processing core. It runs as part of the packet processing loop. So, so that way, we don't have to dedicate a CPU for just doing scheduling, and you just have the packet processing cores which also do the packet scheduling. So we already support full functionality expected out of a scheduler from these software schedulers. So I think we already have that algorithm. We already have done enough amount of testing, and it's a matter of porting that code base to DPDK. So some of the advantages I see with this approach is it's a simple programming model, as in none of the applications need to know that we have a dedicated core for the scheduler. When I say application, I'm not talking only about the packet processing application. I'm talking from the applications from the orchestrator to the end node. That whole breadth of applications. We don't need to reserve any CPU cores. We will have a well-balanced utilization of all the cores, and CPUs would be used. The utilization of the CPU is proportional to the bandwidth. If you need more bandwidth, you throw more CPUs at it, and it is well balanced already. Okay, so the next feature I have is the packet format. So DPDK supports fixed packet format. It defines a packet format of its own. Each buffer can be located randomly in memory, and it represents one packet. So what that means is each packet transfer from the NIC into the memory results in one transaction over the PCI bus. So in our tests, we have seen that this is representing I/O bottleneck. So for example, we ran the L2 forwarding application with Intel 520 NIC cards with 64 byte size packets, and we cannot reach line rate. We are stuck at 79% of the line rate. Even if you add additional CPUs, you cannot go beyond 79%. But if we change the packet size, if we increase the packet size from 64 byte to 128 byte, then we can achieve full line rate. This indicates that we have enough raw bandwidth over the PCI link, but it's to do, the issue is with the number of transactions that are happening over the PCI bus. So looking at the available solutions in the market today, how some of the hardware available out there solves this problem. So there are some NICs that support what I call as the tape mode. So in tape mode, what happens is NIC is provided with pages of memory. It's not provided with one buffer at a time. It's provided with, let's say, 4K pages. And then the NIC goes ahead and writes the packet contiguously, and it coalesces multiple packets into multiple transactions into single transaction. And that way it reduces the number of transactions over the PCI bus. So like what I have shown here, this is one single contiguous space, and the NIC goes ahead and writes the packets contiguously in the memory. And it combines, let's say in this picture, 4 packets into one transaction over the PCI bus. So now, let's say that how do we take this solution into DPDK, right? So we need to have the metadata, we need to have user data, headroom and tailroom. So I think one solution can be that we have the packet data and then a parallel set of metadata, user area, headroom and tailroom. I think that can be one of the solutions. So for each given packet, there is a set of the other data that's associated with that, and that way we could address this issue. So now, looking at what ODP has done in this space. So ODP does not define any packet format of its own. It defines abstract packet data type. So this allows each SoC and NIC to have its own packet format. I think that's good, but I'm questioning if that's the ideal solution. We have seen that not having that fixed metadata, it results in us writing APIs to access the metadata. And depending on your application needs, those APIs we might not be able to inline them. So we would incur extra CPU cycles in order to access the metadata. And then packet processing requires frequent access to the packet metadata. What it means is you are going to call these APIs again and again and again. So I think we need to take a hybrid approach. The hybrid approach would be a fixed metadata, as in all the hardwares would follow a fixed set of metadata. So that would allow us to inline the metadata APIs, metadata access functions. And that would save us the CPU cycles associated with calling functions. And then we also need to provide flexibility in separating the packet data and the metadata. Like I showed in the previous slide, we have a set of packet data and then the metadata. So having the separate set of packet data would allow the NICs to follow the tape mode, and then having the fixed metadata would save us with the CPU cycles. But today, I think that the APIs and the metadata structure in DPDK supports this design. I think that capability exists today. But we have to see, DPDK obviously supports a lot more use cases. So we have to see, I still haven't looked at what all needs to be done in order to solve various use cases. One of the use cases is the what IO drivers. So the other question I want to ask is, or I would like everyone to think about is, can we have NICs that produce packets with the format that we want, like a DPDK format, for example, in the tape mode? That is, the packets coming out of the DPDK are already in this format. It has metadata, user area, headroom, and then there is packet data, and then space for the expanding the packet. But this packet is generated in the tape mode, where what I mean by that is the NIC generates the required format, and it puts them contiguously and coalesces the transactions into multiple transactions into single transaction. So I don't know whether that's the good solution, but that's something for us to think about. We already see solutions from different vendors wherein they are generating the packet with the required metadata and these various fields coming out of the hardware, so that the drivers don't have to spend CPU cycles writing this metadata. So I'm thinking maybe this is the next extension to that work. So these are few of the features that I have been thinking that it would be useful to move them or port them to DPDK. I'm sure there are other features that might be of interest for the ODP community. Feel free to provide any feedback on those features. So this is all I had for today. So any questions, concerns?
So the use of inline data or inline APIs is really a function of whether they're part of the ABI.
Yes.
Right.
Yeah.
So DPDK currently does define an ABI, okay,
Yes.
but it does so in a way that basically says, here's a pointer to the data, and you can rely on this struct, and so
Yes.
go rummage around to your heart's content.
Yes.
Do you see that as problematic, or something that if you move if you move that into a formalized ABI, you can have the access functions that still get automatically inline, so you get the same performance, but without the lock-in that a defined struct requires.
Yes. So I talked about depending on the application requirement, right? So some of the applications might need this ABI compatibility, and some of the applications might not. So when you need the ABI compatibility, you cannot inline the functions.
Well, no, that's the point, is that if it is defined to be part of the ABI, you can always say inline. You can also, if it's not part of an ABI, then you can only inline if you don't care about ABI compatibility.
So when we talk about ABI compatibility, right? So in DPDK, the ABI compatibility is for the access functions, metadata access functions, right? So now if the application cares about ABI compatibility, then it has to take the overhead of calling the functions. Whereas in DPDK, the ABI compatibility is that structure. The structure is the ABI compatibility. So over there, even though the application has to care about ABI compatibility, it will not take the overhead of calling functions. So I think that, well, I agree to an extent that is this structure that we define today will solve all our problems in the future. That question remains. But if we think that, hey, is this structure enough for us, then I think maybe that's a good solution. So I think, in my opinion, that hybrid approach of having fixed metadata and the flexibility of writing packets wherever you want in the memory, I think that's a better solution, is my opinion. But yeah.
We had a lot of discussion about this metadata and user area, and what is the size of user area, and which hardware can support what. So everything it depends. So ODP just described general case when everything is hidden under API, and it's
Yes.
up to implementation how decided. DPDK is more common for NICs, and looks like Intel NICs is good with that. Our
Yes.
NICs should follow Intel or do something
Yes.
else, right? Or break ABI.
So I agree to some extent. I think DPDK has the capability today that allows some amount of flexibility. So if we look at the metadata of DPDK, it has got a pointer to the buffer, and I think that that's kind of enough, or at least that gives that flexibility today to have your packet data in a separate area and your metadata in a separate area. So I think it provides that flexibility. I'm sorry, did I answer your question?
Yeah. Well, it's not. It was not just a question. It's just a comment
Okay. Yeah.
for your question.
Yeah, I think there is some amount of flexibility, but we need to work with the NICs that support the alternate model, the tape model, and see how we can solve some of the other use cases that are that DPDK solves. For example, one of the use cases that I have been pointed out is the vhost and VirtIO use case. So I believe that's more similar to, I'm not an expert on that, but my understanding is that's more similar to the slot mode. So if we have a hardware that supports tape mode, how do we take these packets and transfer to the application running in the guest? I think that's something that needs to be explored more. Okay, any other questions? Okay, good. We are right on time. Thank you very much.